Apollo 11 was not a victory lap after John F. Kennedy's promise. It was a dangerous bargain in which the United States publicly chose a goal before it knew exactly how to achieve it. That is the uncomfortable truth at the center of the moon landing. The famous words came first. The machinery, procedures, engines, computers, flight rules, landing judgments, and rescue margins had to follow. A president could stand before Congress and make the destination sound clean, land a person on the moon, and return him safely to Earth before the decade was out. But the sentence contained two promises, not one. Reaching the moon would be spectacular. Coming home would be mandatory. And between those two verbs, landing and returning, there would be no simple pause button. By the time Apollo 11 left Earth, the mission still held a kind of early escape route. NASA notes that Apollo 11 flew a free return trajectory before lunar orbit insertion, a path that gave the spacecraft a passive way back toward Earth if the mission did not continue into lunar orbit. But that safety narrowed with each commitment. The burn toward the moon, the arrival behind it, the descent of Eagle away from Columbia, the computer alarms, the rough terrain below, the fuel remaining, Neil Armstrong's hand on the final approach. The first footprint was not waiting at the end of a parade. It was waiting at the end of a chain. The chain began in public on May 25, 1961, when President John F. Kennedy addressed Congress and asked the nation to commit itself to a lunar landing before the decade ended. His goal was precise enough to be remembered in one line: landing a person on the moon and returning him safely to Earth. It was also large enough to require a new national machinery of invention. The timing was not accidental. NASA identifies the Cold War space race as central to Kennedy's decision. The Soviet Union had already changed the sky. In 1957, Sputnik became a symbol that the contest between superpowers had moved above the atmosphere. It was a small spacecraft with an enormous political echo. A machine in orbit could be heard as a message. Technical capability was now visible over every border. Then, on April 12, 1961, Yuri Gagarin orbited Earth. A human being had gone into space, and he was not American. The event sharpened the pressure on the United States in a way that was technical, political, and psychological at the same time. It suggested that rockets were no longer only weapons or research instruments. They were declarations. They could show the world who could organize industry, science, risk, and national purpose at the highest level. Kennedy's lunar commitment answered that pressure by choosing a goal so difficult that it could reset the terms of the rivalry. Not merely an orbit, not merely a first in space, a landing on another world, followed by a safe return across the same distance. That last phrase mattered. Returning safely to Earth prevented the promise from becoming only spectacle. It forced the mission to be judged as an engineering system, not a symbolic gesture. The lunar landing had to include the way back from the start. Every design choice carried the weight of that sentence. A rocket had to lift the crew from Florida. A spacecraft had to cross the quarter-million-mile gulf to the moon. A separate craft had to descend to the surface. Another spacecraft had to wait in lunar orbit. The two had to meet again. And the part that survived re-entry had to bring 3 men through Earth's atmosphere and into the ocean. The public heard a destination. Engineers heard a sequence of irreversible acts. That is why Apollo 11, the mission that finally carried the promise to the moon, cannot be understood as a single event. The launch on July 16, 1969, would become one of the most watched departures in history. The landing in the Sea of Tranquility on July 20th would become one of the most quoted arrivals. The first step, early on July 21st, Coordinated Universal Time, would become one of the most replayed human gestures ever recorded. But the title of this story points to the pressure inside the clock, the 102 hours between launch and the first footprint. Strictly, the landing itself came at about 102 hours and 45 minutes of ground elapsed time. Armstrong's first step came later, after post-landing checks and preparation, at about 109 hours and 24 minutes ground elapsed time in NASA's event record. The phrase 102 hours belongs most closely to the descent and landing, not the boot print. And that distinction matters because the moon landing was not completed when Eagle touched down. Touchdown ended one danger and opened another chapter of work. Still, the first 102 hours carried the mission from ignition on Earth to the moment when the crew could say that the lunar module had landed. It was the span in which Kennedy's sentence became mechanical reality. By 1969, the abstract challenge had names. Neil Armstrong was the commander. Michael Collins was the command module pilot. Edwin Buzz Aldrin was the lunar module pilot. Their spacecraft had names too. Columbia for the command module, Eagle for the lunar module. Those names would become familiar, almost mythic. But before they were mythic, they were pieces of a complex flight plan. Columbia and Eagle would have to separate, dock, undock, descend, reunite, and begin the journey home. The mission depended on choreography conducted across distances where hesitation could become fatal. It also depended on institutions built to absorb complexity. Kennedy Space Center in Florida would become the departure point. Mission Control would become the listening mind on Earth. NASA's records would later reduce immense moments to times, maneuvers, and ground-elapsed minutes. Launch, Earth parking orbit, translunar injection, lunar orbit insertion, powered descent, touchdown. The calm precision of those records can hide the wager beneath them. The wager was that the United States could make the extraordinary repeatable enough to trust. It could build a launch vehicle powerful enough to leave Earth. It could guide a crew across space. It could place them in lunar orbit. It could lower 2 of them toward an airless surface. It could manage alarms from the guidance computer and still judge whether the landing could continue. It could bring Eagle down when the planned landing site had slipped away beneath the spacecraft and rough terrain near West Crater was coming into view. This was not only a rivalry of flags, it was a rivalry of systems. The Cold War gave the moon race its urgency, but the mission itself was fought against physics, distance, heat, vacuum, fuel limits, memory limits, and human workload. Sputnik and Gagarin had made space a public arena. Kennedy had made the moon a national deadline. Apollo 11 would have to make that deadline real without losing the crew inside the machinery of the promise. There is a quiet severity in Kennedy's wording that can be easy to miss. He did not simply say the United States should go to the moon. He said it should land a person there and return him safely to Earth before the decade ended. That meant the mission would not be measured by liftoff alone, or arrival alone, or even by the first footprint. It would be measured by completion. If the crew did not come home, the promise would fail at its final word. So the first chapter of Apollo 11 is not the roar of engines. It is the decision to create a moment that would require the roar of engines. It is a public commitment made under Cold War pressure after Soviet achievements had made the heavens politically visible. It is the transformation of national anxiety into an engineering deadline. And it is the beginning of a story in which every triumph created the need for the next, more dangerous success. By the morning of July 16, 1969, that promise had become hardware standing on the Florida coast. At Kennedy Space Center, on Pad A at Launch Complex 39, the vehicle assigned to Apollo 11 waited with a formal identity, Apollo Saturn Vehicle AS-506. It was 363 feet tall, held down before release and built around power on a scale few human inventions had ever displayed. The promise had left the language of speeches. It was now bolted, fueled, wired, and aimed at the sky. By the time the promise reached the Florida coast, it no longer sounded like a speech. It had mass. It had height. It had engines. It had a place on a launch pad and a vehicle number in NASA's records. Kennedy Space Center was the American edge of the attempt. Not the moon, not yet, but the last firm ground beneath the mission. On July 16, 1969, Apollo 11 stood at Pad A, Launch Complex 39, at Kennedy Space Center in Florida. The launch vehicle was not only called Saturn V. In the formal language of the mission, it was Apollo Saturn Vehicle AS-506. That identity matters because Apollo 11 was never simply a symbol waiting to rise. It was a particular machine, assembled for a particular flight, with a specific burden. AS-506 had to do more than leave Earth. It had to lift 3 astronauts, 2 spacecraft, fuel, guidance systems, life support equipment, and the layered hopes of a decade into a path precise enough to make the moon reachable. The public saw a rocket. NASA saw a stack of obligations. The Saturn V assigned to Apollo 11 stood 363 feet tall. That figure is easy to hear and hard to feel. It was taller than many buildings, but unlike a building, It was not meant to stand. Its purpose was to destroy its own stillness. Every tank, engine, structure, wire, and instrument existed for a sequence of events that would begin with restraint and then release. It was built to be held down until the final moment, and then to convert stored chemical energy into motion faster than the human senses could comfortably measure. At the base of that vehicle were 5 F-1 engines. Together, at liftoff, they produced about 7.5 million pounds of thrust. The number has the blunt quality of industrial fact, but it describes something almost theatrical in scale, force great enough to begin moving the tallest and most powerful launch vehicle ever brought to operational service for Apollo's lunar attempt. The 5 engines were the first public violence of the mission. Before lunar orbit, before the descent alarms, before Armstrong's judgment over a boulder field near West Crater, the entire story depended on whether those engines could turn the still machine on Pad A into a rising one. This is why the launch pad itself belongs in the story. Pad A at Launch Complex 39 was not scenery behind the rocket. It was the meeting point between Earthbound engineering and a planned departure from Earth. Until launch, the Saturn V was part of the Cape landscape, fixed against the Florida sky. After launch, if every stage did its work, Apollo 11 would first enter an Earth parking orbit and only later be aimed toward the Moon. But at Pad A, all of that future remained compressed into a vertical stack. The scale of the Saturn V can make it seem inevitable in hindsight, as if a machine of that size had only one possible destiny. But Apollo 11's rocket was not a monument. It was a temporary arrangement. It would not go to the Moon intact. Its job was to spend itself. The launch vehicle had to create the conditions under which smaller machines could take over. First, it had to lift the Apollo spacecraft away from Florida. Then the mission would depend on upper stage performance, orbital timing, translunar injection, docking, navigation, lunar orbit insertion, and a separate lunar descent vehicle that would later be called Eagle. So the Saturn V's size was not excess. It was the cost of the method. NASA's lunar landing plan required a sequence in which one vehicle would launch everything, but not everything would land. The great rocket on Pad A carried the machinery that would later separate into more delicate roles. The command and service module would have to carry the crew through deep space and back toward Earth. The lunar module would have to descend to the surface and rise again from it. Those spacecraft were still hidden within the larger launch configuration, not yet acting as Columbia and Eagle in the drama the world would remember. On the pad, their future identities were enclosed inside the Saturn V's purpose. That is part of the quiet tension in the image of AS-506 before launch. The vehicle was enormous, but the mission's success would eventually narrow down to much smaller spaces: a cockpit, a guidance display, an engine burn, a docking tunnel, a landing radar, a crew decision made in seconds. The Saturn V made the lunar landing possible by creating the first great translation, from a place on Earth to a path around Earth. But it could not complete the landing. It could only deliver the mission to the next set of risks. The rocket's height and thrust also reveal the rivalry embedded inside the engineering. Apollo 11 came from a political promise made under Cold War pressure, but by July of 1969, that rivalry had been converted into testable machinery. The competition was no longer only a contest of announcements, firsts, and national prestige. It had become a contest of systems that had to work in the physical world. A launch vehicle either generated enough thrust or it did not. A guidance plan either placed the spacecraft where it needed to be or it did not. A spacecraft either survived the sequence or it did not. The Saturn V was the visible answer to that pressure. It was not an abstract claim that the United States could reach the Moon. It was the means chosen to begin proving it. Still, there is something almost deceptive about a rocket on its pad. It looks complete. It suggests finality. In photographs and memory, Apollo 11 often appears frozen at this moment, white against the sky, a machine already famous before it moves. But the stillness hides the fact that the mission had not yet done anything that mattered most. It had not reached orbit. It had not restarted its third stage for the Moon. It had not turned Columbia around to dock with Eagle. It had not crossed the middle distance. It had not entered lunar orbit behind the Moon, where Earth could not listen in real time. It had not separated the two spacecraft, begun powered descent, or faced the alarms that would come before landing. All of that was still ahead. The rocket on Pad A was a beginning shaped like a conclusion. At 363 feet, Saturn V gave Apollo 11 its first form, towering, formal, numbered, and held in place. With 5 F-1 engines and about 7.5 million pounds of liftoff thrust, it gave the mission its first power. But it did not give the mission its human judgment. That would come from the three men seated above the engines, enclosed within a spacecraft that had not yet become the center of the story. For the moment, they were part of the stack. Commander Neil Armstrong, Command Module Pilot Michael Collins, and Lunar Module Pilot Edwin Buzz Aldrin were carried by the same machine toward the same first departure. But the architecture around them already contained division. One spacecraft would be Columbia. One would be Eagle. One man would remain in lunar orbit while two descended. The giant on Pad A was the machine that could lift them all together, but Apollo 11 would succeed only if, later, its parts could separate and find one another again. The giant on Pad A could lift the mission, but it could not simplify it. Apollo 11 was never one object going to one place. It was a chain of machines and decisions carrying three men whose work would soon separate into different kinds of solitude. At the top of the Saturn V, above the fuel, above the engines, above the structure that NASA identified as Apollo's Saturn vehicle AS-506, sat the crew, Neil A. Armstrong, Michael Collins, and Edwin Buzz Aldrin. Their names would become inseparable in memory, often spoken as a single unit. But the mission did not treat them as interchangeable passengers. It assigned each man a role, a place, and eventually, a different view of the moon. Armstrong was commander. That title sounds simple, almost ceremonial, until the architecture of Apollo is understood. The commander was responsible for the conduct of the mission and, for Apollo 11, would be the person in the left-hand seat of the lunar module during the descent to the surface. When Eagle came down toward the Sea of Tranquility, when the planned landing point slipped away and rough terrain appeared ahead, it would be Armstrong who took partial manual control and guided the spacecraft toward a safer place. That moment was still more than 100 hours away. On the pad, he was still enclosed in the launch stack. But his future responsibility was already built into the seating, the training, and the flight plan. Collins was command module pilot. His spacecraft was Columbia, the command and service module, identified in the flight plan as CSM-107. Of the two named spacecraft, Columbia was the one that had to come home. It would carry all three men away from Earth, travel with Eagle toward the moon, enter lunar orbit, and then, after separation, become the waiting vessel above the surface. While Armstrong and Aldrin descended, Collins would remain alone in lunar orbit, circling the moon in the only part of Apollo 11 that would return to Earth. That fact gives his title its weight. Command Module Pilot did not mean observer. Collins would be responsible for the spacecraft that kept the route home alive. Columbia was not a backdrop to the landing. It was the mission's refuge, engine room, navigation platform, and return vehicle. The Smithsonian National Air and Space Museum now preserves Columbia in its collection, describing a machine built by North American Rockwell, made primarily of aluminum alloy, stainless steel, and titanium. But on July 16, 1969, it was not yet an artifact. It was the working spacecraft that had to survive launch, translunar coast, lunar orbit, rendezvous, and the journey back through Earth's atmosphere. Aldrin was Lunar Module Pilot. The title can mislead, because the lunar module would be flown as a crewed spacecraft, and Armstrong, as commander, would have a central role in the landing. But Aldrin's position tied him closely to the systems of Eagle, the lunar module identified in the flight plan as LM-5. Eagle was not shaped like an airplane, not built to fly through air, and not meant to return to Earth. It was a spacecraft for a place without atmosphere, a descent machine and ascent machine made for the moon alone. If Columbia was the craft that preserved the route home, Eagle was the craft that made the landing possible at all. It had to be carried folded inside the spacecraft lunar module adapter during launch. It had to be extracted after translunar injection. It had to remain dormant and then come alive. Armstrong and Aldrin would enter it through the docking tunnel during the coast to the moon, checking the machine that looked fragile because it did not need to survive wind or ocean or runway. Its world was vacuum, gravity reduced to fraction of Earth's, and a landing site selected from orbit and photographs, but finally judged through windows by human eyes, watching by orbit aprons' prolific weight. The names Columbia and Eagle gave the mission a public language. They were easier to hold in the mind than CSM-107 and LM-5, but both kinds of names mattered. The nicknames made the spacecraft characters in the story. The formal identifiers kept them inside the discipline of engineering, inventory, procedure, and flight control. Apollo 11 depended on both worlds, the symbolic and the exact. Columbia, in the American imagination, carried older meanings of nation, exploration, and travel. Eagle carried the image of descent, precision, and national emblem. Yet the mission did not succeed because the names were poetic. It succeeded only if the two vehicles performed a sequence that left little room for romance. They would launch together. They would enter Earth orbit together. They would be sent toward the moon together. Then, Columbia would separate from the third stage, turn around, dock with Eagle, and pull it free from the adapter that had protected it during launch. Later, near the moon, the pair would enter lunar orbit. Later still, Eagle would undock and descend, leaving Columbia and Collins overhead. After the surface stay, Eagle's ascent stage would have to lift off from the moon and find Columbia again in lunar orbit. Only after docking and transfer could the landing crew return to the command module. Then Eagle would be left behind, and Columbia alone would carry the astronauts home. This was the central wager of lunar orbit rendezvous. Apollo 11 did not send one large craft down to the moon and back up again. Instead, it carried two spacecraft because each could be optimized for a different part of the journey. Columbia was built for deep space travel, lunar orbit, and Earth return. Eagle was built for landing and leaving the lunar surface. The choice reduced what had to descend to the moon, but it added the drama of separation and reunion. The path to the first footprint required the crew to trust a plan in which survival depended on machines parting company in lunar orbit and finding one another again. That trust was not abstract. Every role pointed toward a future moment when the crew would no longer be sitting together in one cabin. Armstrong and Aldrin would be inside Eagle, descending toward an area chosen as relatively flat and safe in the Sea of Tranquility. Collins would be inside Columbia, passing around the moon, sometimes beyond direct contact with Earth. The three-man crew would become a pair and a single man, divided by function, distance, and the shape of the mission. Before all that, they were still together. On the morning of launch, the public saw a crew. NASA saw a crew, two spacecraft, and a flight plan filled with separations that had to become dockings, dockings that had to become transfers, and transfers that had to become return. The Saturn V could provide the first violent act, but it could not complete the story. Its purpose was to place Columbia, Eagle, and the three men on the opening path. There is a quiet tension in that arrangement. The mission began as unity. One rocket on one pad, one countdown, one crew. But its success would be measured by controlled division. Columbia and Eagle had to leave Earth as hidden parts of a single stack, then become independent vehicles with different destinies. Armstrong, Collins, and Aldrin had to depart together, then accept that the moon would separate their work. For the moment, nothing had yet moved. Pad A still held the full weight of the vehicle. The spacecraft names were still future call signs, waiting to enter the airwaves. The formal identities, CSM-107 and LM-5, sat inside binders, checklists, and procedures. Above the engines, the crew waited inside the machine that would soon stop being a monument and become a motion. At 1332 UTC on July 16, 1969, that motion would begin. The careful architecture of roles and vehicles would be carried upward in fire, leaving Kennedy Space Center for the first test of the journey, reaching Earth orbit. The motion began exactly where the previous stillness had ended, on Pad A, at Launch Complex 39, with the crew already sealed above the machinery that had carried the weight of a national promise for 8 years. At Kennedy Space Center, the morning of July 16, 1969, had a public time and emission time. For the people watching from Florida, and for millions following the countdown at a distance, the launch came at 9:32 in the morning Eastern Daylight Time. In the language of the flight record, it was 1332 UTC. That conversion matters because Apollo 11 was already becoming more than a local event. It was taking place in Florida, but it would be tracked, timed, and judged in a frame larger than any coastline. At that instant, the Saturn V assigned to Apollo 11, Apollo Saturn vehicle AS-506, stopped being a structure on the pad and became a departing vehicle. Until then, its scale could be measured against towers, service arms, roads, and human bodies. 363 feet of rocket had stood vertical on the coast, a white and black column carrying Columbia, Eagle, and the three men whose work had been divided before it had even begun. But a rocket at rest is still partly understandable. It has surfaces. It has platforms beside it. It has a place. A rocket in flight belongs to another category. The first force came from the bottom of the stack, from the 5 F-1 engines of the Saturn V first stage. NASA Kennedy describes their combined liftoff power as about 7.5 million pounds of thrust. The number is almost too large to serve the imagination, but it can be understood by what it had to overcome. It had to lift not only metal and fuel, not only the command and service module Columbia and the Lunar Module Eagle hidden above, but the entire architecture of Apollo's first departure from Earth. It had to turn a machine held on the ground into a machine committed to the sky. There was no moon landing yet in this moment. There was not even a moon-bound spacecraft in the practical sense. There was only the first necessary act: leave Earth, survive the climb, and arrive in orbit with enough order remaining for the next decision. That distinction is easy to lose because history remembers Apollo 11 from the direction of its ending. It remembers Armstrong on the lunar surface. It remembers Eagle at Tranquility Base. It remembers the first footprint. But on the morning of July 16th, none of that could be reached by romance or declaration. The landing depended first on the work of acceleration. The crew had to be carried upward through the first violent transition from a launch pad in Florida to a path around Earth. Inside the spacecraft stack, Neil Armstrong, Michael Collins, and Buzz Aldrin were not yet separated by the mission's later geometry. Armstrong was not yet the commander guiding Eagle over lunar hazards. Collins was not yet alone in Columbia in lunar orbit. Aldrin was not yet standing beside Armstrong on the surface. Their roles were already defined, but for launch, they were three men inside one upward-moving system, trusting that each layer below them would do its work before being left behind by the mission's progress. The world outside the spacecraft changed faster than any speech could follow. Pad A dropped away. Kennedy Space Center became landscape. Florida became coastline. The Atlantic became a reference beneath them. The Saturn V was not merely rising, it was beginning to exchange one kind of motion for another. On the pad, it had been vertical and waiting. In flight, it had to become both upward force and forward speed. Reaching space was not enough. Apollo 11 had to enter orbit. That first orbit was the real target of the launch phase. NASA describes Apollo 11's initial Earth parking orbit as approximately 114 by 116 miles. The shape of that phrase is quiet compared with the spectacle of liftoff. It sounds administrative, almost modest, an orbit measured in two close altitudes, a narrow path above the planet. But for the mission, it was the difference between a launch and a successful beginning. A parking orbit meant Apollo 11 had not been thrown blindly at the moon. It meant the spacecraft had reached a controlled path around Earth, where its speed and position could be assessed before the next burn. The mission was still close to home, but no longer part of the ground. It was in the temporary middle state Apollo required, no longer a vehicle on a launch pad, not yet a vehicle on a lunar trajectory. That middle state had been built into the plan. The Saturn V did not simply rise from Florida and point directly at the moon in one continuous gesture. Apollo's route depended on sequence. Launch first, Earth orbit next. Then, only after the spacecraft and its upper stage had completed about 1.5 circuits of Earth, the S-4B third stage would be called on again for the burn that would send Apollo 11 out toward the moon. But that later act had not yet arrived. The chapter of fire was still resolving into the calmer geometry of orbit. The violence of launch had a particular purpose. It was not destruction, though it looked and sounded like controlled catastrophe. It was a disciplined transfer of energy into a vehicle that had to leave the atmosphere and become precise. Everything about Apollo 11 depended on this change from raw power to measured motion. The five F-1 engines at liftoff supplied the first overwhelming force, but the success of the launch would be judged not by flame alone. It would be judged by whether Columbia, Eagle, the crew, and the remaining rocket stage arrived in the right orbit for what came next. The initial parking orbit was close to circular by the standards of the mission description, approximately 114 by 116 miles. It was not the destination. It was a waiting room moving around Earth at orbital speed. Beneath Apollo 11, the planet still filled the mission's immediate reality. The crew had not escaped Earth's influence. They had entered a path around it, one carefully chosen so that the spacecraft could pause without stopping. That is one of the quiet paradoxes of the early mission. Apollo 11 was moving enormously fast, yet in mission logic it was waiting. The launch had ended the long public suspense of the countdown, but it had opened a more technical suspense. The spacecraft had reached orbit, but the moon had not yet been chosen by engine burn. The crew had left Kennedy Space Center, but they were still bound to Earth until the next major maneuver. For the people on the ground, this was also a shift in how the mission would be understood. A launch can be watched. It rises in view, with sound delayed across distance and flame visible even to those far from the pad. Orbit is harder to see. It is known through tracking, communication, and numbers. The event becomes less like a spectacle and more like a procedure unfolding over the curve of the planet. And Apollo 11 was now fully inside that procedural world. The names Columbia and Eagle still described spacecraft whose full independence lay ahead. Columbia had not yet separated and turned around to dock with Eagle. Eagle was still enclosed in the stack. Not yet the lunar machine Armstrong and Aldrin would enter during the coast. Not yet the craft that would descend toward the Sea of Tranquility. But both had survived the first requirement. They had been carried from Earth into the orbit from which the lunar journey could be attempted. The launch at 1332 UTC did not complete Kennedy's promise. It did not land anyone on the moon, and it did not return anyone safely to Earth. What it did was narrower and indispensable. It proved, for this mission and this crew, that the enormous machine on Pad A could perform the first act in the chain. It could lift Apollo 11 out of Florida and place it into the measured path NASA described as approximately 114 by 116 miles above Earth. From there, the mission entered a quieter interval. The rocket no longer needed to demonstrate itself by rising from the pad. The spacecraft no longer belonged to the horizon. It circled Earth, carrying 3 men, 2 spacecraft, and one remaining question that would soon become unavoidable. Apollo 11 was in orbit. The moon was still waiting. And before the crew could leave Earth behind in any deeper sense, the parking orbit had to do its brief, essential work. The quiet after launch was not a pause in the mission. It was one of its designed movements. Apollo 11 had not gone directly from Pad A toward the moon because the journey was not a single throw. The Saturn V had first done something more measured. It had placed the spacecraft into Earth orbit, into the track NASA described as approximately 114 by 116 miles above the planet. That orbit was not the destination, and it was not a failure of ambition. It was a waiting room with velocity. It gave Apollo 11 a brief interval in which Earth remained close, the moon remained untouched, and the next decision could be prepared with extraordinary care. The phrase parking orbit can sound almost gentle, as if the spacecraft had been set aside. But nothing about it was still. Columbia, Eagle, and the remaining upper stage of the Saturn V were moving around Earth at orbital speed, held in a balance between falling and missing the ground. The Atlantic, Africa, the Indian Ocean, the Pacific, and the Americas were no longer regions on a map below them. They became a rotating surface, clouded and curved, passing under the spacecraft as the mission kept to its narrow mathematical path. For the crew, this was the first sustained experience of the mission after the violence of ascent. Neil Armstrong, Michael Collins, and Buzz Aldrin were no longer being driven upward through the atmosphere by the full stacked force of the Saturn V. The first stage was gone. The second stage was gone. The spacecraft and the S-IVB third stage had reached a temporary orbit together, still connected in the arrangement that would soon matter more than any view out the window. Apollo 11 was not yet the pair of spacecraft people remember from the coast to the moon. Columbia had not yet turned around. Eagle had not yet been pulled free from its place inside the spacecraft Lunar Module adapter. The mission still had the long shape of launch, command and service module, lunar module hidden below it, adapter panels around the fragile lander, and the S-4B stage behind them as the last major engine in the Saturn V sequence. The architecture of separation and docking was waiting. Before that could happen, the third stage had one more job. That job is why the parking orbit mattered. If the rocket had simply tried to aim straight from launch toward the moon, the entire act would have been compressed into one enormous, continuous demand. Instead, the mission used Earth orbit as an intermediate step. First, reach space. First, prove that the launch vehicle had placed the spacecraft on the planned path around Earth. First, let the mission settle into a known orbit. Then, at the proper time, use the S-IVB again. The moon was not just far away. It was moving. Earth was rotating. Apollo 11 was moving. The departure for the moon had to happen from the right place in the orbit, at the right moment, with the spacecraft pointed and accelerated into a path that would intersect the moon's future position, not merely its place in the sky. The parking orbit gave the mission a way to separate these problems. The ascent from Florida had brought Apollo 11 into low Earth orbit. The next burn would choose the route outward. That separation of tasks was one of Apollo's quiet strengths. The public drama had been the launch. The engines, the flame, the sound across the coast, the white rocket rising from Kennedy Space Center. But the moon mission was not won by spectacle alone. It depended on staging, timing, restart capability, navigation, and on the willingness to treat Earth orbit not as a destination, but as a platform. There is a psychological change inside this part of the flight. During launch, the crew rode a controlled explosion away from the pad. In parking orbit, they were already beyond the atmosphere, yet still close enough to Earth to feel its dominance. Earth filled the story. The moon was not yet a place they were falling toward. It was an objective still waiting behind a maneuver. The spacecraft's orbit, approximately 114 by 116 miles, was low by the standards of the distance still ahead. The moon lay hundreds of thousands of miles away. Against that distance, the parking orbit was almost a skim above Earth, a thin, circular ledge just beyond the reach of the atmosphere. Apollo 11 had left the ground, but it had not yet escaped the planet's hold in the way the mission required. That distinction matters. Orbit is not departure from Earth. Orbit is a form of captivity that looks like freedom. The spacecraft was falling around the planet, and unless something changed its speed and path, it would continue to circle. The S-IVB restart would be that change. The third stage had already helped lift Apollo 11 into orbit. Now it had to ignite again and transform a circle around Earth into a path toward the moon. The restart was not ceremonial. It was an irreversible deepening of the mission. Before it, Apollo 11 was in Earth orbit. After it, the spacecraft would be on its way outward. The next burn would not land anyone on the moon, but it would make the moon the defining body in the story ahead. It would commit the spacecraft to a translunar coast and set up all the later acts: Columbia's separation and turnabout, docking with Eagle, extraction of the lunar module, the long passage through the middle distance, and eventually the engine burn behind the moon that Earth could not watch. For now, though, the mission circled. The crew carried the names and roles already assigned to them: Armstrong as commander, Collins as command module pilot, Aldrin as lunar module pilot. Their two spacecraft carried names as well, although one of them was still enclosed and unseen in its launch position. Columbia would be the homeward ship. Eagle would be the machine of descent. In parking orbit, those futures were present but not yet active. The mission had all of its pieces, but it had not yet rearranged them into the form required for lunar flight. The world below was still the world that had made the promise. Kennedy Space Center was already behind them. The Cold War urgency, the public commitment, the engineering discipline, and the immense industrial chain that had produced Apollo Saturn vehicle AS-506 had all been translated into motion. But the flight had entered a zone where ambition had to become procedure. There was no single heroic gesture that could replace the timing of the next engine burn. After about 1.5 Earth orbits, the waiting would end. The S-IVB, quiet now, behind the spacecraft, would be called on again. Its restart would last only minutes, but those minutes would decide whether Apollo 11 remained a satellite of Earth or became a spacecraft bound for the moon. So the parking orbit held the mission in suspense, not the suspense of inaction, but of alignment. Earth turned beneath Apollo 11. The moon waited ahead. The third stage moved with them in silence, carrying the last great push of the Saturn V. The first act had lifted them from the pad. The second would choose their direction. The first act had lifted them from the pad. The second would choose their direction. In the parking orbit, Apollo 11 was still moving with Earth. It had crossed the threshold into space, but it had not yet escaped the planet's hold in the way the mission required. The spacecraft was circling above the same world that had launched it, tracing an orbit NASA described as approximately 114 by 116 miles. That orbit was not the destination. It was the platform from which the next decision would be made by machinery, mathematics, and timing. The Saturn V had one major task left. Behind Columbia and Eagle, still attached to the spacecraft, was the S-IVB third stage. During launch, it had helped place Apollo 11 into Earth orbit. Now it waited for its restart. This was the stage that would perform translunar injection, the burn that would send the spacecraft out of Earth orbit and onto a path toward the moon. The phrase can sound clinical, as if the moon were a target on a diagram and the spacecraft were simply pointed at it. But translunar injection was not a shot in the simple sense. Apollo 11 was not fired at the place where the moon appeared to be. It had to be placed on a route through moving gravity fields toward a moon that was also moving, with Earth falling away behind it. The burn had to add enough speed in the right direction at the right moment so that the spacecraft would leave its temporary orbit around Earth and enter the long coast across the middle distance. After about 1.5 Earth orbits, the moment arrived. The S-IVB reignited. For roughly 5 minutes, the quiet architecture of the parking orbit became acceleration again. The third stage was no longer simply carrying the spacecraft around Earth. It was changing the mission's geometry. The burn length was short compared with the days ahead, and small compared with the immense public scale of the launch. But in mission terms, it was one of the defining acts. Before it, Apollo 11 was an Earth satellite. After it, the spacecraft was committed to the translunar coast. This was not yet the same kind of commitment that would come later at the moon. NASA notes that Apollo 11 used a free return trajectory before lunar orbit insertion. That detail matters because it shows how the mission's boldness was surrounded by layers of caution. In the early outbound phase, before the spacecraft deliberately entered the moon's gravity well, the trajectory offered a passive return option. If later events prevented the normal plan from continuing, the path itself could bring the spacecraft back toward Earth without requiring the crew to perform the full sequence of lunar operations. A free return trajectory did not make the mission safe in any absolute sense. Nothing about Apollo 11 was absolute safety. The spacecraft still depended on functioning systems, life support, navigation, communications, and the ability to survive the return environment. But the route gave the mission a built-in mercy. Before lunar orbit insertion, the spacecraft had not yet made the burn that would bind it to the moon. It was on a path that could, if necessary, curve around the moon and send it home. That is the quiet tension inside translunar injection. It was the burn that chose the moon, but it did not yet close every door behind the crew. NASA's description of Apollo 11 as the last Apollo mission to fly a free return trajectory before lunar orbit insertion places this choice in a larger technical history. Later missions would accept different trajectories to serve different landing goals. Apollo 11, the first landing attempt, carried a more conservative path into the unknown. The mission could aim for the moon while preserving, for a time, a way back that did not depend on landing there. In the cabin, Neil Armstrong, Michael Collins, and Buzz Aldrin were riding the consequence of a stage that had already done more than most machines ever do. The S-IVB had helped them reach orbit. Now, with its restart, it was giving them the velocity needed to leave that orbit. The men were not yet separated into their later roles, Armstrong and Aldrin descending in Eagle, Collins circling alone in Columbia. At this point, they were still together at the head of the stack, carried by a single chain of hardware that began at the command module and ran back through the lunar module, the adapter structure, and the third stage. The mission still had the look of something launched as one object. But that condition was almost over. Translunar injection changed more than speed. It changed the meaning of the spacecraft's parts. The Saturn V, which had dominated the story from Pad A through Earth orbit, was approaching the end of its central role. The rocket that had been the public symbol of power was becoming a spent instrument. The mission would soon depend less on spectacle and more on spacecraft handling, separation, rotation, docking, extraction, navigation, and the long discipline of coast. The burn also changed the psychological scale of the flight. Low Earth orbit still kept Apollo 11 close to home in a way that could be imagined. The crew passed above Earth again and again, held in a loop. Translunar injection opened that loop. The spacecraft was no longer circling the planet in the same closed path. It was moving outward, onto a route where Earth would diminish and the Moon would become a destination rather than an object in the sky. For the people in mission control, the burn was a measured event, governed by data. For the world watching, it was harder to see. There was no tower of flame rising from Florida now, no bright column lifting from the coast. The decisive action was occurring in space, above the atmosphere, as an engine fired on a vehicle already too distant for ordinary sight. Apollo 11's great public beginning had been visible. Its departure from Earth orbit was more abstract, but no less important. The exactness mattered because the mission did not have the luxury of brute force after launch. The Saturn V had been massive, but the journey to the Moon depended on using velocity carefully. Too little energy, and the spacecraft would not be placed properly on its translunar path. Too much, or in the wrong direction, and the route would demand correction. Apollo was an invention of engines, but it was also an invention of timing. Translunar injection was where those two truths met. As the S-IVB burn continued, Earth's gravity did not suddenly release the spacecraft like a cut rope. Gravity still shaped the path. The burn gave Apollo 11 enough energy to climb away from Earth orbit and fall along a new trajectory, one that led outward toward the Moon. The spacecraft would coast most of the way. The engine firing was brief. The consequence would last for days. And within that consequence was a careful balance between commitment and restraint. Apollo 11 was now outward bound. It had left the parking orbit behind. Yet before lunar orbit insertion, it still retained the free return character that NASA identifies as part of the mission's early design. The spacecraft was headed for the Moon, but the Moon had not yet captured it. The most dangerous commitments still lay ahead. The burn behind the Moon to enter lunar orbit, the undocking of Eagle from Columbia, the descent toward the Sea of Tranquility, and finally, the decision to continue through alarms, rough terrain, and dwindling margins. For now, the key fact was simpler and immense. The S-IVB had done its work. The 5-minute burn had transformed Apollo 11 from a spacecraft circling Earth into a spacecraft on the way to another world. But the journey could not continue as the launch stack had been assembled. Eagle was still enclosed inside the spacecraft Lunar Module adapter. Columbia was still facing away from the lunar module it would soon need to retrieve. The machine that had left Earth as a narrow tower now had to rearrange itself in space. The burn had chosen the Moon. The next task was to turn the spacecraft around and make the two vessels ready to travel there together. The burn had chosen the Moon. Now Apollo 11 had to change its shape. The Saturn V had done what only the Saturn V could do. Its third stage, the S-4B, had restarted after the parking orbit and pushed the spacecraft onto the translunar path. But the vehicle that left Earth was not yet the vehicle that could land on the Moon. It was still arranged for launch, not for lunar flight. Columbia, the command and service module, was mounted at the front of the stack. Behind it, hidden inside the spacecraft Lunar Module adapter, was Eagle, the lunar module. Behind them both was the spent third stage that had just supplied the great push away from Earth. That arrangement made sense inside the atmosphere and during ascent. It kept the lunar module protected. It kept the stack narrow and strong. It allowed the rocket to rise as one machine from Pad A at Launch Complex 39. But once translunar injection was complete, the logic changed. Apollo 11 no longer needed to behave like a launch vehicle. It needed to become a spacecraft system. The moon landing depended on two vessels, not one. Columbia would carry the crew across deep space, enter lunar orbit, and later bring them home. Eagle would descend to the surface and rise again to meet Columbia. If Eagle remained sealed inside the adapter, it was only cargo. If Columbia could not reach it, dock with it, and pull it free, the central design of the mission would fail before the crew ever came near the moon. So, after one of the most dramatic burns of the flight, the next essential act was almost architectural. The spacecraft had to rearrange itself. NASA describes the sequence plainly. After translunar injection, the Command and Service Module Columbia separated, turned around, docked with the Lunar Module Eagle inside the spacecraft Lunar Module adapter, and extracted it for the coast to the moon. And that sentence is one of the most delicate transformations in Apollo 11. The launched stack became a paired spacecraft. The hidden lander became an active companion. The path to the moon became more than a trajectory. It became an arrangement that could make a landing possible. Michael Collins, the command module pilot, had a central role in this maneuver. That role was built into the title he carried. Armstrong commanded the mission. Aldrin was the lunar module pilot, but Collins was responsible for Columbia as a spacecraft in its own right. At this moment, Columbia was no longer simply the forward part of the launch stack. It had to separate, move away, turn, approach, connect, and extract. The sequence began with separation. Columbia pulled free from the S-4B and the adapter assembly that still enclosed Eagle. In visual terms, Apollo 11 was beginning to unmake the tower that had left Florida. The Command and Service Module moved out ahead, creating the room needed for the turn. It was a small motion compared with the launch and the translunar burn, but it carried a different kind of risk. The crew was now working in free space, with the moon ahead and Earth already receding behind them. The booster could no longer solve problems by brute force. The spacecraft had to be handled with precision. Then came the turn. Columbia rotated to face the vehicle it had just left. The command module's nose, which had been pointed away from Eagle during launch, was brought around toward the lunar module waiting in the adapter. In the language of the mission, this was transposition, the command and service module changing orientation so it could return to the lunar module and dock. The maneuver sounds almost simple when reduced to the word turn, but its importance was enormous. Apollo's lunar mission was built around rendezvous and docking. That would matter later in lunar orbit, when Eagle would have to return from the surface and meet Columbia. Here, on the way out from Earth, the first major docking of the mission had to prove that the two spacecraft could become one traveling system. Eagle, at this point, had not yet looked like the spacecraft history remembers standing on the Sea of Tranquility. It was still inside the spacecraft Lunar Module adapter, the structure that had carried it beneath Columbia during launch. The adapter was not the destination. It was packaging for the climb through the atmosphere and the acceleration into space. The lunar module had been protected there because it was never meant to fly through air. It was built for vacuum, for lunar orbit, for descent and ascent near the moon. Its usefulness began after Earth had been escaped. That is why extraction mattered. Docking was not only a connection, it was the act that allowed Eagle to be taken out of its launch cradle. Columbia approached, aligned, and joined with the lunar module. Once docked, the paired spacecraft could pull Eagle free from the adapter. The lander was no longer enclosed cargo. It was attached to the command and service module, ready to travel toward the moon as part of the mission's working architecture. There's a quiet rivalry hidden in this maneuver, not between astronauts, but between design choices. A mission to the moon could be imagined in different ways. Apollo 11's actual path depended on separate spacecraft doing separate jobs, one to remain in lunar orbit, one to land and return from the surface. That choice made the launch mass possible, but it also made docking essential. The mission did not carry a single vehicle that could do everything from Earth to the lunar surface and back. It carried Columbia and Eagle, each incomplete without the other at the critical moments. This is why the extraction after translunar injection was more than housekeeping. It was the first time, after leaving Earth orbit, that Apollo 11 took on the form it would need for the rest of the outward journey. Columbia was the crew's main cabin, navigation platform, and return vessel. Eagle was the machine that would attempt the descent. Together, docked nose to nose, they became the spacecraft that would coast across the middle distance between Earth and Moon. The timing also mattered because the mission was still early in its translunar flight. NASA notes that Apollo 11 flew a free return trajectory before lunar orbit insertion, giving the spacecraft a passive return option before the later commitment to the moon's gravity well. That did not make the journey safe in any ordinary sense. It did mean that, at this stage, the path itself still carried a measure of contingency. But that trajectory alone could not land anyone. The physical arrangement of the spacecraft still had to be correct. The free return path could help bring the crew home if major plans changed, but it could not retrieve Eagle from the adapter. That task belonged to the spacecraft and the crew. After extraction, the old launch stack was no longer the center of the story. The S-4B had performed its last major duty for Apollo 11 by sending the spacecraft out of Earth orbit. The mission now belonged to Columbia and Eagle. One had been built to carry the astronauts through the long passage and back through Earth's atmosphere at the end. The other had been built for a place without air, where landing legs and a descent engine mattered more than streamlining. Their connection was temporary, but essential. They would travel joined together until lunar orbit brought the next separation. In the cabin, the maneuver would have been understood not as spectacle, but as procedure. Apollo 11's public image often moves from launch directly to the moon, from flame to footprint. But the actual mission was full of intermediate acts that had to succeed without grandeur. This was one of them. No one could stand on the lunar surface unless Columbia first turned around in space. No one could descend to the Sea of Tranquility unless Eagle was pulled free and carried there. The boldest promise of the mission depended on a careful mechanical rearrangement after the rocket had already done its loudest work. The transformation was now complete. Apollo 11 was no longer a spacecraft attached to a spent rocket stage with a lander buried behind it. It was a docked pair, Columbia and Eagle, crossing outward together. The mission had passed from launch configuration into lunar flight configuration. The next stretch would be quieter, measured less by violence than by checks, navigation, and waiting. Ahead lay the long coast through the middle distance. Eagle had been extracted, but it still had to be trusted. Before anyone asked it to descend toward the moon, Armstrong and Aldrin would need to inspect the fragile-looking machine from the inside, passing through the docking tunnel during the translunar coast. For now, though, the essential change had happened. Columbia had turned. Eagle had been freed. And the two spacecraft that would divide the work of Apollo 11 were finally traveling together toward the moon. Columbia had turned. Eagle had been freed. And now, with the two spacecraft joined nose to nose, Apollo 11 entered a quieter kind of risk. The violence of launch was behind them. The restart of the S-4B was behind them. The delicate turn, docking, and extraction were behind them. What remained, for the moment, was distance. Earth was falling away. The moon was no longer just a target in the flight plan, but the body toward which every calculation, every instrument reading, and every human decision was now converging. This was the translunar coast, the long middle distance between the planet that had built Apollo 11 and the world on which it was meant to land. It is easy to remember Apollo 11 as a sequence of visible events. The launch, the docking, the landing, the first step. But the mission depended just as much on the hours between those events, when the work was quieter and the drama moved inside the spacecraft. During the coast to the moon, Columbia and Eagle were not simply drifting. They were being watched, checked, understood, and prepared. By this point, Apollo 11 was in the configuration it needed for the rest of the outward journey. Columbia, the command and service module, was the crew's main living and operating spacecraft. Eagle, the lunar module, was attached at the docking tunnel, still untested in the environment that mattered most. It had been carried into space as cargo, hidden inside the spacecraft lunar module adapter. Now it was exposed, docked, and traveling as a partner. But a partner had to be trusted. Eagle was a strange-looking machine, even by the standards of spacecraft. It was not built to fly through air. It did not need wings, streamlining, or the smooth aerodynamic shell that Earthbound flight had trained people to expect. Its shape belonged to a different world, a vacuum, a place where descent would be governed by engine thrust, guidance, radar, gravity, and judgment. To human eyes, it could appear fragile, angular, almost unfinished. But every part of it had a purpose because the lunar module had one task no other vehicle had ever completed: separate from a mothership in lunar orbit, descend to the moon, support two astronauts on the surface, and then lift them back to rendezvous with Columbia. That task was still days away. And that was precisely why the checkout mattered. On July 18th, during the translunar coast, Neil Armstrong and Buzz Aldrin entered Eagle through the docking tunnel. The date sits quietly in the mission timeline, far from the thunder of the Saturn V and far from the voice that would later call from Tranquility Base. Yet this passage through the tunnel was one of the acts that made the landing believable. The commander and the lunar module pilot went into the spacecraft that would soon become their descent craft, their surface shelter, and their ascent vehicle. Michael Collins remained with Columbia, the spacecraft that would have to bring the crew home. The division of responsibilities that had existed on paper was becoming physical. Armstrong and Aldrin were the men who would fly Eagle down. Collins was the command module pilot, responsible for Columbia, the craft that would remain in lunar orbit when the mission divided. During the coast, however, the three were still together, still connected, still operating a combined spacecraft. The separation was coming, but not yet. The tunnel between Columbia and Eagle was more than a passageway. It was a promise that the two spacecraft could operate as one system until the moment they had to become two. It represented the engineering logic of the whole Apollo method. Instead of landing the entire spacecraft on the moon, NASA had chosen lunar orbit rendezvous. The command and service module would remain in orbit. The lunar module would descend. Then the ascent stage of the lunar module would return from the surface and meet Columbia again. That future rendezvous depended on docking hardware, hatches, pressure integrity, crew procedures, and confidence built long before the moon filled the windows. So Armstrong and Aldrin's entry into Eagle was not ceremonial. It was inspection. It was preparation. It was a rehearsal of trust. Inside, the lunar module was not a roomy vessel. It was a working machine designed around the needs of descent and ascent, not comfort. Its identity in the flight plan was LM-5. It carried the name Eagle, but the name did not soften the reality. This was the first lunar module that would be asked to land human beings on the moon. Earlier missions had tested pieces of the architecture. Apollo 10 had flown near the moon and surveyed the landing region from about 10 miles above the surface. But Eagle would be the first to attempt the final descent. The July 18th checkout therefore belonged to a special category of mission work. It did not make a headline in the way launch did. It did not produce a single iconic sentence. It was not a dramatic burn behind the moon or a last-minute decision over boulders. But it reduced uncertainty. It allowed the astronauts to see, touch, and evaluate the machine they would soon depend on. It let mission control and crew treat Eagle not as an object extracted from the adapter, but as a spacecraft being readied for flight. The coast itself created a deceptive calm. Outside the windows, the spacecraft was crossing the space between worlds. Inside, the mission remained procedural. The crew and the controllers on Earth were bound together by checklists, communications, navigation, and the steady discipline of not assuming that a spacecraft was healthy merely because it was quiet. In Apollo, silence did not mean simplicity. It meant that the next danger might still be forming beyond sight in a valve, a circuit, a reading, a trajectory, or a human assumption. This was also the last part of the journey before the mission would begin to lose one of its great protections. NASA describes Apollo 11 as the last Apollo mission to fly a free return trajectory before lunar orbit insertion. That meant that, during the early outward coast, the path still offered a passive return option before the spacecraft committed to lunar orbit. It was not a guarantee against disaster, but it was an important feature of the route. If the mission did not perform the later commitment maneuver, the trajectory itself could help carry the spacecraft back toward Earth. That protection gave the middle distance its own tension. Apollo 11 was moving toward the moon, but not yet fully captured by it. The mission was approaching a threshold. Until lunar orbit insertion, the path still had a built-in way home. After that, the crew would be inside the moon's gravitational theater in a different, more committed sense. The first landing attempt required the spacecraft to cross that boundary. Every quiet check during the coast pointed toward that decision. Columbia had already proven essential. It had carried the crew, performed the turn, and docked with the lander. Eagle had now been freed and entered. Its inspection gave Armstrong and Aldrin a more direct relationship with the vehicle that would carry them away from Collins and toward the lunar surface. The mission was still one spacecraft in operational terms, but the story had begun to separate into its future parts: Columbia as the returning ship, Eagle as the landing craft, and the 3 men as a crew that would soon divide by role and by distance. There was a kind of restraint in this phase that can be easy to miss. Apollo 11 was not racing in the human sense. It was following a planned route, shaped by launch energy, celestial mechanics, and timed maneuvers. The crew could not hurry the moon closer. Mission Control could not make the next major event arrive sooner. They could only use the time well. That is what the translunar coast was for. It was for confirming that the spacecraft were still capable after the violence of departure. It was for making the lander familiar before it became necessary. It was for preserving attention across hours when nothing spectacular seemed to be happening, because the spectacular moments would not forgive neglect. The future landing in the Sea of Tranquility would depend not only on Armstrong's hand in the final descent, not only on Aldrin's instruments and callouts, not only on Collins keeping Columbia ready in orbit, but on this quieter work done days before in the middle distance. By July 18th, Apollo 11 was no longer close to home in any ordinary sense, but it was not yet at the moon. Earth and moon held the spacecraft between them, one world receding, the other drawing nearer. The crew had crossed into Eagle and returned to the shared rhythm of the docked spacecraft. The fragile-looking machine had been inspected from within. Trust had not been assumed. It had been built, checklist by checklist, hatch by hatch, through the tunnel between Columbia and Eagle. Ahead, the calm would narrow. On July 19th, Apollo 11 would reach the far side of the moon, where direct radio contact with Earth would be cut off. There, hidden from mission control, the spacecraft would have to fire its engine for the first lunar orbit insertion maneuver. NASA's event record would place that burn at 75 hours, 55 minutes, 52 seconds ground elapsed time. But before that unseen commitment, there was this passage outward, a coast through darkness and sunlight, through procedure and waiting, with Eagle attached and the moon growing nearer. The moon was no longer a destination ahead of them. By July 19th, it had become terrain, gravity, shadow, and risk. Apollo 11 had crossed the middle distance with Columbia and Eagle joined together, the two spacecraft moving as one toward the body that would soon hide them from Earth. For most of the flight, distance had not meant silence. The crew could speak with mission control. Telemetry could flow back to Houston. Controllers could watch systems, compare numbers, listen to voices, and turn uncertainty into procedure. Even when the spacecraft was far from Earth, it was still inside a chain of communication. But the moon would break that chain. The first lunar orbit insertion maneuver had to be performed while Apollo 11 was behind the moon, out of direct radio contact with Earth. It was a simple sentence, almost clinical in the mission record, but it carried one of the deepest anxieties of the flight. The engine burn that would decide whether Apollo 11 entered lunar orbit could not be watched in real time by the people on Earth whose lives had been built around watching everything. NASA's Apollo 11 lunar event record places the maneuver at 75 hours, 55 minutes, 52 seconds ground elapsed time. By then, the spacecraft had left behind the launch tower, the parking orbit, the S-4B restart, the docking and extraction of Eagle, and the long coast outward. It had also left behind the earlier protection of a free return path. NASA notes that Apollo 11 was the last Apollo mission to fly a free return trajectory before lunar orbit insertion, a trajectory that offered a passive return option before the spacecraft committed itself to lunar orbit. That phrase, before lunar orbit insertion, is the threshold. Until then, the moon could be passed, its gravity used rather than entered. After the burn, Apollo 11 would no longer be simply flying past the moon on a path shaped for return. It would be captured. To be captured by the moon was the mission's requirement. Armstrong and Aldrin could not descend to the Sea of Tranquility from a flyby. Collins could not wait for them in Columbia unless Columbia first became a lunar orbiting spacecraft. Eagle could not separate, descend, and later climb back to rendezvous unless all of this took place inside a carefully shaped orbit around the moon. The landing depended on the orbit. The orbit depended on the burn. And the burn would happen where Earth could not listen. There is a particular kind of tension in a machine doing exactly what it was designed to do, but doing it beyond sight. Apollo 11 did not lose contact because something had gone wrong. It passed behind the moon because the mission required it. The far side was not a failure of communication. It was a wall placed there by geometry. The moon itself stood between spacecraft and planet. For the crew, the moment belonged to the spacecraft and the checklist. Neil Armstrong, Michael Collins, and Buzz Aldrin had lived through days of tightly sequenced operations. They had watched Earth shrink behind them and the moon grow ahead. They had inspected Eagle through the docking tunnel on July 18th, proving confidence in a machine that still had not been asked to land. Now the command and service module, with Eagle attached, had to perform the burn that would turn approach into orbit. For mission control, the same moment belonged to waiting. Houston could prepare. Houston could calculate. Houston could know when loss of signal would come and when the spacecraft should emerge. But during the hidden minutes, mission control could not hear the crew describe the burn. It could not watch the live stream of data confirm each expected change. It could not intervene if the reality on board began to diverge from the plan. The controllers had to trust the work already done, the trajectory design, the navigation, the spacecraft systems, the crew training, and the engine that would fire on the far side of the moon. That trust was not abstract. It had been manufactured over years in engineering reviews, simulations, factories, test stands, and mission rules. The Saturn V had delivered Apollo 11 out of Earth's atmosphere. The spacecraft Lunar Module Adapter had released Eagle. Columbia had turned, docked, and extracted the lunar module. The joined spacecraft had survived the coast. Every previous success had earned the right to attempt this one. But none of those successes could make the hidden burn routine. The first lunar orbit insertion maneuver had to slow Apollo 11 enough for lunar gravity to take hold. In the broadest sense, the spacecraft had to give up some of its forward speed relative to the moon. If it did not slow properly, it could miss the planned orbit. If it slowed too much or too little, the geometry of everything that followed would change. The upcoming separation of Eagle and Columbia, the descent preparation, and the path down toward the Sea of Tranquility all depended on arriving in the right orbital condition. A moon landing is often imagined as a vertical drama, a craft descending, dust rising, legs touching the surface. But before there could be any downward motion toward the surface, Apollo 11 had to become a traveler around the moon. Lunar orbit was the platform from which the landing attempt would be staged. It was also the shelter in which Michael Collins would remain while Armstrong and Aldrin took Eagle away from Columbia. That future was already inside this burn. Behind the moon, Columbia and Eagle were still joined. Armstrong had not yet guided Eagle toward boulder-strewn terrain. Aldrin had not yet called out descent data in the final approach. Collins had not yet become the solitary pilot circling above the far side, while the other two were on the surface. But the shape of that later loneliness, that later division of labor, began here. Lunar orbit made it possible for the mission to split. On Earth, the absence of signal would have had its own sound. Not silence in the room exactly, because mission control was never truly silent. There were loops, consoles, status checks, clocks, and men watching time. But the spacecraft itself was gone from direct contact. The human voices from Columbia were absent. The stream of confirmation was absent. The event had moved beyond the immediate reach of the room built to manage it. The calmness of the official record can hide this. NASA's Lunar Event Record gives a time: 75 hours, 55 minutes, 52 seconds, ground elapsed time. A timestamp fixes the maneuver in history. It makes it searchable, comparable, orderly. But lived from the ground, that time was also a suspense. The burn was either taking place or had taken place. The spacecraft was either being captured by lunar gravity or it was not. Mission Control would know only when Apollo 11 came back from behind the moon and the chain of communication was restored. This was one of the paradoxes of Apollo. The mission was a triumph of communication, computation, and coordinated control, yet some of its most decisive acts occurred beyond immediate human supervision from Earth. The spacecraft had to be capable of acting where Earth was temporarily absent. The crew had to be capable of carrying the procedure through. The ground had to be capable of letting them disappear. And then Apollo 11 emerged with the mission changed. The exact experience of that reappearance belongs to the mission record and the voices preserved from the flight, but the consequence is clear. The spacecraft that had been on its way to the moon was now in lunar orbit. The journey had crossed a boundary that could not be crossed by spectacle alone. It had required a burn hidden from Earth on the far side, at the place where the moon itself blocked the signal. From this point on, the moon was no longer only something Apollo 11 approached. It was the world beneath them, passing below the windows in successive arcs of light and shadow. The mission had entered the region where every later action would be measured against the surface. The Sea of Tranquility was still ahead, not yet a landing site under the footpads, but now it belonged to the operational world of the crew. It was no longer a distant target selected from maps and surveys. It was somewhere below their orbit. The first lunar orbit insertion maneuver did not place a footprint on the moon. It did not separate Eagle from Columbia. It did not produce the sentence the world was waiting to hear from Tranquility Base. Its drama was quieter and in some ways more severe. It was the moment when Apollo 11 accepted the moon's gravity and gave up the last simplicity of merely passing by. The crew still had work to do before any descent. The orbit would have to be refined. Eagle would have to be prepared again, not as an attached machine inspected during the coast, but as a spacecraft soon to fly on its own. Armstrong and Aldrin would move toward their separate task inside the lunar module. Collins would remain with Columbia, the command module that had to bring all three men home. The hidden burn behind the moon made that separation possible. It changed Apollo 11 from an outbound expedition into a lunar operation. Around the moon, the two named spacecraft still flew together for a time, Columbia and Eagle connected as they had been through the coast. But the logic of the mission was already pulling them apart. Soon the joined craft would become two vehicles with different duties, one to descend, one to wait, and both to depend on the orbit one in silence behind the moon. Around the moon, the two spacecraft still looked like one mission joined at a single point. Columbia and Eagle had crossed the long distance from Earth together, and after lunar orbit insertion, they had circled the moon as a connected pair. But the connection was temporary by design. Apollo 11 could not reach the surface as one vehicle. The command and service module was built to orbit, to navigate, to sustain, and finally, to return through Earth's atmosphere. The lunar module was built for a different bargain, to leave that orbit, descend without wings into vacuum, stand on the moon, and then rise again to find Columbia. By about 100 hours and 12 minutes into the mission, that bargain became visible. Eagle undocked from Columbia. It was a quiet mechanical event compared with launch or translunar injection or the hidden lunar orbit insertion burn. There was no tower of flame. There was no departure from Earth. But in the architecture of Apollo, undocking was one of the clearest dividing lines in the flight. Until then, the mission still had the physical reassurance of one combined spacecraft. After undocking, there were two vehicles in lunar orbit, two crews, two sets of immediate responsibilities, and one narrow requirement that could not fail. They would have to meet again. Inside Eagle were Neil Armstrong and Buzz Aldrin. Armstrong, the commander, would fly the lunar module through the descent and make the final decisions when the surface came close. Aldrin, the lunar module pilot, would manage the systems and help guide the machine through the sequence it had been built for. They were moving toward the part of Apollo 11 that the world most vividly imagined, the landing, the ladder, the first step. But before any of that, they were simply two men inside a small spacecraft that had never before been flown to the lunar surface. Inside Columbia was Michael Collins. His task was less visible to the public imagination, but it was absolute. Collins remained in the command module, the spacecraft that had to keep working if Armstrong and Aldrin were to come home. Columbia was not going to land. It would not touch the Sea of Tranquility. It would not appear in the photographs of the first boot prints. Yet it was the indispensable vessel of return, the part of Apollo 11 that would carry the crew back across the distance to Earth. The separation made the roles of the two named spacecraft plain. Eagle now belonged to descent. Columbia belonged to survival after descent. One would risk the surface. One would preserve the way home. There is a particular solitude in Collins's position that has lasted in the memory of the mission. He was alone in lunar orbit while Armstrong and Aldrin prepared for the landing attempt. But that solitude was not passive. He was not merely waiting. Columbia had to remain healthy. Its systems, its orbit, and its readiness mattered with every circuit around the moon. The command module pilot's work was to protect the spacecraft that would have to rendezvous with Eagle after the landing and descent, then carry all three astronauts out of lunar orbit and back toward Earth. That responsibility gave the undocking its deeper tension. Apollo 11 was not a direct descent from Earth to the Moon. It was a chain of inventions and procedures, each dependent on the previous one. The Saturn V had placed a mission in Earth orbit. The S-4B had sent it toward the Moon. Columbia had turned, docked, and extracted Eagle. The combined spacecraft had entered lunar orbit behind the Moon, out of radio contact with Earth. Now the mission depended on lunar orbit rendezvous, the idea that one spacecraft could descend while another stayed above, and that the two could find each other again around another world. After undocking, Armstrong and Aldrin were not yet descending to the surface. There was still time between release and powered descent, and that time mattered. Eagle had to be checked and prepared as an independent spacecraft. It was no longer only a module attached to Columbia. It was now a flying vehicle in its own right, with its own guidance, propulsion, life support demands, and crew procedures. The lunar module's form had always reflected its strange purpose. It did not need to be aerodynamic. There was no lunar atmosphere for wings or streamlining to work against. Its shape could be angular, exposed, almost improbable, because it was designed for vacuum and low gravity. Earlier in the flight, during the translunar coast, Armstrong and Aldrin had entered Eagle through the docking tunnel to inspect it. That checkout had been a rehearsal of confidence. Now the confidence had to become operational. The release from Columbia also changed the emotional geometry of the mission. For most of the journey, the crew had shared one moving world. They were separated by compartments and duties, but they were together in one connected spacecraft. After undocking, Collins could see Eagle outside Columbia, and Armstrong and Aldrin could see the command module from the Lunar Module. The two spacecraft were close, but closeness in orbit is not the same as safety. Every movement had to preserve the carefully planned conditions for the next phase. The Moon below them was no longer an abstract destination. It was passing beneath both spacecraft in gray detail, a landscape of plains, craters, shadows, and glare. Apollo 11's intended landing region lay in Mare Tranquillitatis, the Sea of Tranquility, selected as a relatively flat and safe area. That judgment had been built from survey, planning, and prior reconnaissance, including the work of Apollo 10, which had flown above the Moon and surveyed from about 10 miles up. But no survey could remove the final uncertainties. The landing would still depend on navigation, timing, engine performance, computer guidance, crew judgment, and a view through Eagle's windows. For Collins, the landscape had a different meaning. He would keep circling it. At times, Columbia would pass behind the Moon and lose direct radio contact with Earth, as the combined spacecraft had done during lunar orbit insertion. That recurring silence was part of lunar flight. On the far side, the Moon itself blocked the line to mission control. The crew and spacecraft had to continue without the immediate presence of Houston in their headsets. After undocking, that isolation had sharper edges. Collins was alone in Columbia, behind a world, keeping the return ship alive. The command module's importance can be measured by its ending as much as by its function. Columbia was the only part of the Apollo 11 spacecraft that would return to Earth. Eagle would be used for the lunar landing and ascent, but Columbia was the vessel built to survive the homeward journey and the final passage through Earth's atmosphere. The Smithsonian National Air and Space Museum would later preserve Columbia as an artifact of that return, a North American Rockwell-built command module made primarily of aluminum alloy, stainless steel, and titanium. In lunar orbit, though, it was not an artifact. It was the crew's future. That future depended on Collins holding his part of the mission while Armstrong and Aldrin moved deeper into theirs. In Eagle, the preparation for descent carried a different kind of pressure. The lunar module had to leave the safe companionship of Columbia and commit to a lower path. Its descent engine would soon be used not for spectacle, but for exact shaping of an orbit and then for controlled fall toward the surface. There would be a descent orbit insertion burn behind the Moon, performed out of direct contact with Earth. Later, powered descent initiation would begin at about 102 hours and 33 minutes ground elapsed time. Those events would compress years of design into minutes of flight. But at this point, just after undocking, Apollo 11 was suspended between design and proof. The two spacecraft had separated, but the landing had not yet begun. The plan was still intact. The orbit was still holding. Mission Control still had its procedures. The crew still had its checklists. Yet the mission had changed shape in a way that could not be mistaken. Columbia was alone. Eagle was free. The public story of Apollo 11 often narrows toward the surface, toward the words that would be spoken after touchdown and the footprint that would come hours later. But the first landing depended just as much on this separation in orbit. It depended on a commander and lunar module pilot willing to take a fragile machine downward, and on a command module pilot remaining above in the only spacecraft that could bring them home. The rivalry that had driven the race to the moon had produced not one heroic machine, but a system of machines, divided by purpose and reunited only if every step worked. Below them, the moon kept turning through the windows. Ahead of Eagle lay shadow, ignition, descent guidance, and the unforgiving arithmetic of altitude and velocity. Ahead of Columbia lay waiting, circling, and the burden of return. The mission had become 2 stories now, moving around the same world, one descending toward tranquility, the other holding the path back to Earth. Eagle was free now, but freedom in lunar orbit did not mean independence from the larger design. Armstrong and Aldrin were separated from Columbia, yet every movement of their spacecraft still had to fit an invisible chain of timing, geometry, and judgment. Above them, Michael Collins continued around the moon in the command and service module. Below them, the Sea of Tranquility moved toward the place where a descent could begin. Between those 2 facts lay the narrow work of changing orbit without losing the path home. The lunar module had not been built to fall straight down from the altitude of Columbia. It had to shape its own approach. After undocking, Eagle flew in an orbit that still carried it around the moon, still moving at orbital speed, still governed by the same lunar gravity that had captured Apollo 11 the day before. The first task was not landing. It was lowering the path from which landing would become possible. That maneuver was the descent orbit insertion burn. Like the first lunar orbit insertion maneuver, it took place while the spacecraft was behind the moon, out of direct radio contact with Earth. Mission Control could prepare the crew, check the numbers before loss of signal, and wait for reacquisition. But the burn itself belonged to Armstrong, Aldrin, Eagle, and the systems aboard the lunar module. The moon blocked the radio link. The same far side that had hidden Apollo 11's first commitment to lunar orbit now hid the beginning of Eagle's final commitment toward the surface. It was a quiet kind of suspense. There was no audience view from Earth of a flame starting in darkness. There was no live confirmation at the instant the engine did its work. The descent engine had to fire to change Eagle's orbit, lowering the low point of its path closer to the lunar surface. That lower path would set up the powered descent that followed. If the orbit was not right, then the landing sequence would begin from the wrong place, with the wrong altitude or velocity, and every later correction would become more expensive in fuel, time, and attention. Apollo 11's landing was often remembered as a final vertical descent, a machine hovering above gray dust. But the real sequence began as orbital mechanics. Eagle had to arrive at the right point above the moon with the right speed and orientation before powered descent could even begin. The landing site was not a fixed mark beneath a hovering craft. It was a moving solution, produced by navigation, radar, onboard guidance, engine thrust, crew observation, and the judgment of controllers in Houston. This was why small errors mattered. Around the moon, a slight difference in position or velocity did not remain slight for long. Over the minutes of descent, an error could become a shift of kilometers on the surface. The planned destination lay in Mare Tranquillitatis, the Sea of Tranquility, a region chosen because it appeared relatively flat and safe. It had been surveyed before Apollo 11, including by Apollo 10, from about 10 miles above the moon. Yet the final approach would not be made on a map. It would be made through the lunar module windows, through instruments, through the Apollo guidance computer, and through voices passing between Eagle and Mission Control. The descent orbit insertion burn, hidden behind the moon, was one of those moments when the rivalry that had driven the mission disappeared behind procedure. The contest between nations had demanded a visible triumph, but the path to that triumph was almost entirely made of invisible commitments. A valve had to open. An engine had to produce the expected thrust. A guidance system had to know where the spacecraft was. A crew had to read the spacecraft's behavior correctly. Mission Control had to be ready for the next decision before the next decision arrived. When Eagle came back around from behind the moon, the landing phase had changed character. The lunar module was no longer merely separated from Columbia. It was now on the descent path. Collins remained above, circling in Columbia, but Armstrong and Aldrin had entered the part of the mission where time would begin to compress. The procedures that had been spread across days during the coast from Earth were now concentrated into minutes. The spacecraft had to slow, descend, search, compute, and respond all at once. Powered descent initiation came at about 102 hours and 33 minutes ground elapsed time. That phrase sounds technical and distant, but it marks one of the most concentrated passages of Apollo 11. From launch at Kennedy Space Center to that instant, the mission had been accumulating speed, distance, and commitments. Now Eagle's descent engine began the burn that would carry it down from lunar orbit toward the surface. The engine was not simply braking the spacecraft in a straight line. At the start of powered descent, Eagle was still moving forward around the moon. The descent engine had to reduce that forward motion and guide the vehicle along a planned curve toward the landing area. Too much thrust, too little thrust, or thrust in the wrong direction would change where Eagle would arrive. The spacecraft was spending velocity like currency, converting orbital motion into a path toward the ground. Every second mattered because every second changed the relationship among altitude, range, fuel, and landing site. Inside Eagle, Armstrong and Aldrin were managing a vehicle unlike any airplane and unlike any capsule. It had no wings. It was designed for vacuum, for 1/6 gravity, and for a landing that no human being had ever performed on the moon. The lunar module's descent engine could be controlled to adjust the rate of descent. The guidance system could calculate and command, but the crew still had to understand whether the machine's solution made sense. They had to compare instrument readings with what the moon itself was showing them. In Houston, mission control was not flying Eagle by remote control. The time delay was not the central problem. The deeper issue was that the final descent could not be commanded from Earth in the way a ground operator might steer a test vehicle. Mission control monitored, interpreted, and advised. Controllers watched the data that came across the voice and telemetry loops. They judged whether the trajectory, guidance, and spacecraft systems were still within acceptable limits. Their calls could continue the landing or end it. But the craft was in Armstrong and Aldrin's hands, with the Apollo guidance computer executing its programs and the descent engine carrying out the physical work. The landing sequence therefore became a collaboration under pressure. The computer held the planned guidance. The engine supplied the changing thrust. The crew watched the instruments and, when the moon came into view in the right way, the terrain. Mission control evaluated the stream of information from 250,000 miles away. No single part of that system was enough by itself. A perfect engine would not save a bad navigation solution. A good computer program could not make a boulder field safe. Crew skill could not overcome unlimited fuel loss. The strength of Apollo was not that risk disappeared, but that risk was divided, measured, and answered by overlapping layers of human and mechanical judgment. Yet those layers also created new kinds of strain. The lunar module was asking its guidance computer to perform essential tasks while the descent unfolded rapidly. The crew depended on the display and keyboard, the D-Sky, to communicate with the Apollo guidance computer. Mission control depended on the data that computer and the spacecraft systems helped provide. The descent engine's behavior, the spacecraft's attitude, the radar updates, the navigational state, and the crew's reports were all part of one tightening loop. At about 102 hours and 33 minutes into the mission, there was still no footprint, no flag, no words from the surface. There was only powered descent, a controlled fall being reshaped into a landing. Eagle was moving toward a site chosen for safety, but the difference between a planned site and an actual touchdown point could be measured in more than pride. It could be measured in kilometers, and later it would matter that Eagle was not exactly where the plan expected it to be. The moon below was not an abstraction now. It was terrain. Craters, shadows, slopes, and fields of rock were becoming operational facts. The Sea of Tranquility had been selected because it offered a reasonable chance, not a guarantee. The final approach would test the difference between the surveyed moon and the moon in the window. As powered descent continued, the mission entered its most demanding minutes. The arithmetic of the guidance system, the judgment of the crew, and the confidence of mission control all had to remain aligned. Then, inside that already compressed sequence, the spacecraft began to present a different kind of warning. Program alarms from the guidance computer, unexpected and urgent, appearing when there was almost no spare time to explain them. The warnings arrived inside a descent that already had no room for distraction. Eagle was falling under power toward the Sea of Tranquility, its descent engine shaping a path that had been calculated, checked, and rehearsed, but was now being flown for the first time over the real moon. The crew had altitude, velocity, fuel, attitude, communications, and the lunar surface itself to think about. Mission Control in Houston had streams of data and only seconds to turn them into judgment. Then the guidance computer began to interrupt the landing with alarms. They were not the kind of alarms anyone wanted to hear during powered descent. They came from the Apollo guidance computer, the machine inside Eagle that helped manage the mathematics of landing. Armstrong and Aldrin interacted with it through the D-Sky, the display and keyboard that translated a dense world of programs, verbs, nouns, and numerical readouts into something a crew could use while strapped into a spacecraft. The D-Sky was not a screen in the modern sense. It was an instrument panel language, spare and exacting, built for a time when every bit of computer memory had to justify its place aboard a spacecraft. That constraint mattered. Apollo 11 was not carrying a large, forgiving machine with unused capacity waiting in reserve. Apollo Lunar Surface Journal contributor Peter Adler describes the Apollo guidance computer as having 36,864 15-bit words of fixed memory and 2,048 words of erasable memory. In human terms, that was astonishingly small. In mission terms, it was enough only because engineers had spent years deciding what had to be kept, what could be omitted, and how the computer should behave when too many things asked for attention at once. The first sudden appearance of a program alarm did not announce in plain language what was happening. It did not say, "The spacecraft is safe." It did not say, "The landing can continue." It gave a code. The crew saw and reported a 12:02 alarm. Later, another code appeared, 12:01. During powered descent, Apollo 11 encountered 5 unexpected computer alarms, including these 12:01 and 12:02 program alarms. Each one arrived in a phase of flight where hesitation could become dangerous, and each one forced Mission Control to answer a hard question almost instantly. Was this a warning that the landing system was failing, or was it a warning that the computer was busy? That distinction was everything. The Lunar and Planetary Institute summarizes the reason the alarms did not stop the landing with essential clarity. Mission Control judged them safe to continue because they indicated computer overload, not the loss of essential landing control. The computer was being asked to handle more than it could comfortably process at that moment, but the alarm did not mean that the guidance needed for the landing had disappeared. It meant that the computer's executive system was overloaded and was shedding or postponing lower priority work while preserving the tasks that mattered most. In another context, overload might sound like failure. In the final minutes above the moon, the word carried a sharper edge. The Apollo guidance computer was not simply a calculating machine in the background. It was part of the system that helped Eagle know where it was, how it was moving, and how to shape the descent. If the alarm had meant that the computer could no longer maintain essential control, the landing would have had to be called into question immediately. But if the alarm meant that the computer was protecting the most important tasks by refusing to be stopped by lesser ones, then the alarm was frightening but survivable. That was the judgment Houston had to make. The drama of these alarms is often remembered as a moment of crisis, and it was. But it was also a moment when the design philosophy of the spacecraft was tested in public silence. The computer did not simply freeze. It did not abandon the landing. It announced that it was overloaded, then continued to do the necessary work. The alarm was not comforting, but it was informative. It told the crew and the ground that something was wrong with the workload, while the machine continued to preserve the work that was most essential. Inside Eagle, Armstrong and Aldrin had to keep flying. They could not turn the descent into a classroom. They could not stop the moon from rising in the window. They could ask for guidance, report what they saw, and continue to monitor the machine that was helping them descend. The words from the ground had to be short because the situation allowed no long explanation. Mission Control's judgment came through as a decision to proceed. The alarms had been understood well enough. They were not a reason, by themselves, to abort. That decision depended on people as much as hardware. Apollo 11's landing was often described through machines: Saturn V, Columbia, Eagle, the descent engine, the Apollo guidance computer. But machines do not interpret themselves. In Houston, Controllers had to connect a code appearing during the most dangerous phase of the mission to what they knew about the computer's behavior. They had to decide whether a strange signal was an acceptable warning or a sign that the attempt must end. The Lunar and Planetary Institute's summary captures the result, but not because the result was simple. It was simple only after the right people understood the meaning of the alarm. The codes 1201 and 1202 became famous because they seemed to arrive at the worst possible time. But their real importance lies in what they revealed about the boundary between automation and command. Eagle was not landing itself in the modern sense, detached from the crew and the ground. Nor was it being flown by hand alone. The descent was a partnership among guidance calculations, engine response, crew attention, and mission control decision-making. The computer could carry the arithmetic that human beings could not perform quickly enough in flight. The astronauts could judge what was in the window. Houston could interpret telemetry and decide whether the system remained trustworthy. For a few minutes, the alarms pulled all three parts of that partnership tight. The fact that the alarms did not stop the landing was not an act of bravado. It was not a decision to ignore warnings. It was a decision to classify them correctly. A warning that says the computer is overloaded is serious. A warning that says essential landing control is gone is something else entirely. Mission Control determined that Apollo 11 was facing the first condition, not the second. The essential guidance functions were still being carried. The descent could continue. This is why the alarms belong at the center of the landing story, even though they were not the only problem Eagle faced. They show how little margin remained. They show that the mission's success depended not on an absence of surprises, but on the ability to understand surprises quickly enough. They also show the discipline behind the word go. A go call in that moment was not optimism. It was a compressed technical conclusion, spoken calmly, because there was no time for anything else. Below Eagle, the Sea of Tranquility continued to expand. The landing zone chosen before the mission was becoming a landscape of real shadows and real hazards. The computer alarms had been judged, and they had not ended the attempt. But the spacecraft still had to find a place to touch down. The descent system had survived its unexpected interrogation. Now Armstrong's view through the window would begin to matter even more, because Eagle was not arriving exactly where the plan had expected it to be. The alarms had not stopped the descent, but they had taken place inside a larger problem that was only now becoming visible. Eagle was still flying, still under control, still descending toward the Sea of Tranquility. Yet the moon beneath Armstrong and Aldrin was not simply a target on a chart anymore. It was a surface rising in the windows, marked by craters, shadows, slopes, and rocks. The landing site had been chosen because it was supposed to be among the safer places to attempt the first human touchdown. But safety, at lunar scale, could not be guaranteed from orbit. It could only be estimated. Before Apollo 11 ever left Earth, the Sea of Tranquility had represented a compromise between ambition and caution. NASA needed a place that could be reached by the spacecraft's trajectory, seen under useful lighting, and judged flat enough for the lunar module's landing gear. The first landing could not begin with a region of mountains or deep crater walls. It needed a broad plain, a place where the moon seemed to offer the least resistance to a machine that had never landed there with people aboard. That was why Mare Tranquillitatis, the Sea of Tranquility, mattered. Its name sounded peaceful, almost poetic, but for mission planners, it was a practical selection. It was relatively flat. It had been studied. It had been photographed. It had been examined from orbit by earlier missions, including Apollo 10, which flew above the moon before Apollo 11 and surveyed the area from about 10 miles over the lunar surface. Apollo 10 did not land. Its task was to rehearse much of the architecture of the landing mission without taking the final step. It brought the moon closer to operational reality. It showed what the approach would look like, how the ground track would behave, how the planned descent region would appear from a spacecraft moving through lunar orbit. From that earlier flight, from photographs, from mapping, and from mission analysis, the landing zone became a place of expectation. It was not unknown in the way the far side had once been unknown. It was not a blank disk in a telescope. It was a planned location, embedded in procedures, guidance targets, and crew training. Armstrong and Aldrin were not simply descending toward the moon in general. They were descending toward a particular place in the Sea of Tranquility, one selected as a relatively flat and safe area for the first landing. But the moon does not honor a plan merely because the plan is careful. During the descent, Eagle was not arriving exactly where that plan had expected. A navigation error had carried the lunar module roughly 7 kilometers beyond the intended landing location. On Earth, 7 kilometers can sound modest, a distance across a city or along a road. In a lunar landing, it was a serious displacement. The descent was built around timing, altitude, velocity, and the assumed character of the ground below. To be several kilometers long meant that the familiar, chosen rectangle was slipping behind them. Eagle was approaching terrain that had not been the intended touchdown point. This was the quiet danger behind the final minutes. The spacecraft could be functioning. The engine could be running. Mission Control could be calling, "Go!" The crew could have survived the program alarms. And still, the landing could fail if the place beneath the lunar module was wrong. Ahead lay rough terrain near West Crater. The region included boulder-filled ground, the kind of surface that could turn a successful descent into a damaged or unstable landing. The lunar module had legs, footpads, and a descent engine designed to lower it onto the moon, but it was not built to choose its own safe patch with human judgment. Its guidance system could fly a trajectory. It could manage the descent. It could help bring Eagle down. But it could not look through the window and understand the meaning of a field of boulders the way Armstrong could. That distinction became decisive. Armstrong, seated on the left side as commander, was not a passenger in an automatic landing. Apollo had always depended on layers of control, guidance from the computer, monitoring from mission control, and crew authority inside the spacecraft. In the final approach, with the planned site no longer directly beneath them and the terrain ahead becoming unacceptable, Armstrong took partial manual control. The phrase can sound understated, almost administrative, but in those minutes it meant that human judgment entered the descent in its most direct form. He had to guide Eagle away from the boulder-filled area and toward a safer place to touch down. The scene in the window compressed years of engineering into seconds of visual decision. Every earlier stage had made this moment possible. The Saturn V lifting from Kennedy Space Center, the parking orbit, translunar injection, docking and extraction, lunar orbit, undocking, descent orbit insertion, powered descent initiation, and the computer alarms that Mission Control had chosen not to treat as fatal. Yet none of those achievements could flatten the rocks below. None of them could move West Crater out of Eagle's path. The mission had reached the point where the final obstacle was not distance from Earth, or the violence of launch, or the mathematics of reaching lunar orbit. It was the immediate geography of the moon. The Sea of Tranquility had been selected because it reduced risk. It did not remove it. That is one of the central truths of Apollo 11's descent. The landing site was not a promise. It was a best judgment made from the evidence available. Apollo 10's survey from about 10 miles above the surface had improved that judgment, but it had not turned the moon into an airport. The closer Eagle came, the more the landing zone changed from a mapped region into a field of individual hazards. Craters that had been features in photographs now had rims and shadows. Rough patches now had depth. Boulders now had size and consequence. For Armstrong and Aldrin, the problem unfolded while fuel was being consumed and altitude was decreasing. There was no option to pause the descent while the ground was reconsidered. Eagle was a spacecraft under power, in lunar gravity, committed to an approach that had to end in either touchdown or abort. The crew had to keep the vehicle stable, understand the guidance, listen to mission control, manage the remaining descent, and interpret the surface below. Every action carried a trade. Fly longer to reach safer ground and fuel margin diminished. Set down too soon and the chosen spot might be dangerous. The landing was no longer just a question of reaching the moon. It was a question of choosing which small part of the moon could accept the spacecraft. This is where the rivalry that had driven Apollo becomes almost invisible. The Cold War urgency, the national promise, the race measured against Soviet achievements, all of it had carried the mission to this point. But in Eagle's window, the contest was no longer public. It was not a speech, not a launch, not a broadcast image of a rocket clearing the tower. It was a commander looking at the ground and refusing to land in a place that might destroy the attempt. The invention was not only the lunar module or the guidance computer or the Saturn V. It was the system that allowed a human pilot at the edge of another world to intervene when the planned solution met the actual terrain. Aldrin's role remained part of the same narrow choreography. As lunar module pilot, he supported the descent with readings, procedures, and awareness inside the cabin, while Armstrong looked outward and flew the final path. The two men were enclosed in Eagle, separated from Collins and Columbia above them, separated from Earth by the delay and distance of lunar space, and separated from success by the last few hundred feet of uncertainty. Mission Control could advise and decide whether conditions remained acceptable. But Mission Control could not see exactly what Armstrong saw in the same immediate way. The final choice of ground belonged inside the lunar module. The irony is that the Sea of Tranquility was still doing what planners had hoped, but not at the exact place they had intended. Beyond the roughness near West Crater, Armstrong found a safer area. Eagle continued forward, away from the boulder field, descending toward a place that had not been the precise point selected before launch, but could serve the purpose that selection had always meant to protect. The target had shifted from a coordinate to a survivable patch of lunar surface. In those last moments, Apollo 11 became less like a machine following a script and more like a machine held within a script by human attention. The guidance system had brought Eagle close. The crew had interpreted what closeness really meant. The landing site problem had not been eliminated by planning. It had been answered by judgment under pressure. Below them, the dust-colored plain filled the view. Behind them lay the planned location, now past. Nearby was the rough ground they had avoided. Ahead was the small, safer opening Armstrong had chosen. Eagle was still descending, the engine still firing, the fuel still counting down, the moon no longer a destination, but a surface waiting for contact. The mission had moved beyond the planned site, and now there was only the final act of descent, the moment when the flying would stop, the legs would take the weight, and a new name would enter the map of the moon. The final act of descent was not a grand movement from far away. It was close, low, and intensely local. The moon had ceased to be the pale disk that had drawn Apollo 11 across space. It was now a field of texture beneath Eagle. Dust, shallow relief, shadows, and the safer patch that Neil Armstrong had selected after steering beyond the rough ground near West Crater. The landing was no longer an idea held in speeches, flight plans, or tracking data. It had become a question of contact. Inside Eagle, Armstrong and Buzz Aldrin were still in a machine that had never landed on the moon before. Every earlier stage of Apollo 11 had reduced uncertainty without removing it. The Saturn V had done its work. Columbia and Eagle had crossed the distance together. The spacecraft had entered lunar orbit. Eagle had separated from Michael Collins and Columbia. The descent engine had fired. The guidance system had absorbed the burden of navigation, and Mission Control had chosen to continue through unexpected program alarms. But none of those achievements could substitute for the last seconds. Until the landing probes and footpads met the surface, Apollo 11 was still flying. The place below them was Mare Tranquillitatis, the Sea of Tranquility. Before the mission, it had been chosen because it appeared comparatively flat and safe, a landing area that gave the first attempt a better chance of success. Apollo 10 had surveyed the region from about 10 miles above the moon, adding confidence to the maps and photographs used by planners. But the descent had carried Eagle roughly 7 kilometers beyond the planned landing location. The selected region remained the Sea of Tranquility, but the exact place had become something more immediate than a surveyed ellipse. It was the ground Armstrong could see, evaluate, and choose while the engine continued to burn. That distinction mattered. Apollo 11 had been designed around systems, guidance, propulsion, communications, radar, flight control, and the coordination between the spacecraft and Mission Control in Houston. Yet the landing showed that systems and human judgment were not rivals. They were layered defenses against failure. The Apollo guidance computer had brought Eagle near the moon. Mission Control had interpreted the 1201 and 1202 alarms as signs of overload rather than the loss of essential landing control. Armstrong, looking through the window, had judged that the place directly ahead was not acceptable and had flown on towards smoother ground. By this point, the descent was compressed into a narrow band of time. The lunar module was low enough that the idea of landing had become physically unavoidable, but not so low that all danger had passed. The engine had to keep Eagle from falling too fast. The crew had to preserve control while avoiding hazards. The vehicle's landing gear had to take the load in a gravity field weaker than Earth's but still utterly real. The event that the world was waiting for would be quiet compared with launch. There would be no flame trench, no tower cleared, no roar across Florida. The final proof of the descent would be the absence of motion. At approximately 20 hours, 17 minutes UTC on July 20th, 1969, the last descent ended. NASA's lunar event record lists the landing at 102 hours, 45 minutes, 43 seconds ground elapsed time. Measured from the launch at Kennedy Space Center, from Pad A at Launch Complex 39, that was the moment when the journey's first great promise reached the lunar surface. Not the first step, not yet the human footprint, but the landing itself. The point at which Eagle stopped being a spacecraft descending toward the moon and became a spacecraft standing on it. The phrasing of that record is spare, almost clinical. Lunar landing. 102 hours, 45 minutes, 43 seconds. It compresses into a line the years of work that had made the moment possible. It also shows why the title of the mission's middle passage matters. The 102 hours between launch and landing were not merely travel time. They were a chain of commitments, leaving Earth orbit, crossing open space, entering lunar orbit, dividing the crew between two spacecraft, beginning powered descent, continuing through alarms, passing beyond the planned site, and bringing Eagle to rest. Then Armstrong spoke. "Houston, Tranquility Base here. The Eagle has landed." The words did several things at once. They reported success to Mission Control. They confirmed that Eagle was down. They gave the landing site a name, Tranquility Base. In that instant, the Sea of Tranquility was no longer only a mare on the near side of the moon, no longer only a landing region chosen by planners and examined from orbit. It had a human point of reference. A base did not mean a settlement, not in the practical sense. Eagle was a fragile lunar module with two astronauts inside, dependent on systems that still had to work if they were to leave. But the name carried the authority of arrival. It marked a place where human beings had brought a machine down, under control, on another world. The response from Earth was part relief, part recognition. Mission Control had followed the descent through data and voice, through alarms that had to be judged quickly, through the knowledge that the landing site had shifted from the plan. The controllers could not look out Eagle's window. They could not see the boulders Armstrong avoided or the exact patch he chose. They had to trust the crew, the instruments, and the rules built through simulation and engineering discipline. When the announcement came, it told them that the descent problem had been solved, not in theory, but in fact. Still, the landing was not the end of Apollo 11. It was the end of one danger and the beginning of another set of tasks. Armstrong and Aldrin were on the moon, but they were also far from home inside a vehicle that had to serve as shelter, work site, and ascent craft. Michael Collins remained in lunar orbit aboard Columbia, alone in the command module that would have to receive Eagle again if the crew were to return. The mission's architecture had always depended on reunion. A successful landing was necessary, but it was not sufficient. That is why this moment should be held carefully. Popular memory often lets the landing and the first footprint collapse into a single event, as if the words, "The Eagle has landed," and the first step onto the surface happened in one continuous breath. They did not. NASA's event record places touchdown at 102 hours, 45 minutes, 43 seconds ground elapsed time. Armstrong's first step would come later, after post-landing checks and preparation, at about 109 hours and 24 minutes after launch. Between those two times lay hours of procedure, caution, and anticipation. The distinction makes the landing more powerful, not less. It shows that Apollo 11's triumph was not a single cinematic instant, but a sequence of thresholds. Launch was one threshold. Translunar injection was another. Lunar orbit was another. Undocking was another. Powered descent was another. Touchdown at Tranquility Base was perhaps the most delicate of all so far, because it joined the immense and the intimate, a national objective declared years earlier, and a small spacecraft settling onto a chosen patch of lunar ground. For Armstrong and Aldrin, the moon was now outside the walls of Eagle, close enough to enter through a hatch, but still separated by procedure, pressure, equipment, and time. The surface that had filled their windows was silent beneath them. The engine was no longer carrying them downward. The alarms had not stopped them. The rough ground had been avoided. The planned site had been passed, but the mission had found a landing place. Tranquility Base had landed. And for the first time in the flight, the next great act would not be about reaching the moon. It would be about opening the spacecraft, descending the ladder, and placing a human foot onto the world that Eagle had just touched. The moon had been reached, but it had not yet been entered. Inside Eagle, the first moments after landing were not a celebration in the ordinary sense. They were checks, confirmations, and disciplined restraint. The descent engine had shut down. The landing legs held. The spacecraft that had just flown over craters and boulders was now a small, pressurized room standing on another world. Armstrong and Aldrin were alive, but they were still inside a machine that had to keep them alive. The first footprint would have to wait. That waiting mattered. Apollo 11 had not been designed as a single dramatic instant. It was a chain of survivals. Launch had to work. Translunar injection had to work. Docking had to work. Lunar orbit insertion had to work. Undocking, powered descent, guidance, communication, and landing had all had their turn. Now the sequence had narrowed to a hatch, a ladder, a suit, a surface, and the question of whether human beings could work safely outside Eagle in the lunar environment. The time between touchdown and the first step was almost 6 hours and 40 minutes. In public memory, the landing and the footprint often seem nearly fused, as if Armstrong spoke from Tranquility Base and then immediately descended into history. But NASA's event record separates the two moments clearly. Eagle landed at 102 hours, 45 minutes, 43 seconds ground elapsed time. Armstrong was listed on the lunar surface at 109 hours, 24 minutes, 15 seconds ground elapsed time, corresponding to 02:56:15 UTC on July 21, 1969. In those hours, the mission changed from flight to fieldwork. Armstrong and Aldrin first had to make Eagle safe after landing. They worked through post-landing procedures, verifying the state of the lunar module and preparing for the possibility of an emergency liftoff if the spacecraft proved unstable or unsafe. The same vehicle that had brought them down would have to lift them back into lunar orbit. Beneath their boots was the moon, but above them, somewhere beyond the black sky, Michael Collins continued around the moon in Columbia. The landing was historic, but it was not enough. The two spacecraft still had to reunite. Only after the immediate checks could the astronauts turn fully toward the extravehicular activity, the EVA. The words sound technical, and they are. An EVA was not a walk in the casual sense. It was a controlled departure from a life-supporting cabin into an environment with no breathable air, no easy rescue, and no tolerance for casual mistakes. Armstrong and Aldrin had to configure suits, life support equipment, communications, and the cabin itself. Eagle had to be depressurized before the hatch could open. The moon was close, but procedure stood between closeness and contact. When the hatch was opened, the next movement became intensely physical. Armstrong had to back out of the lunar module, move carefully onto the porch, and descend the ladder attached to Eagle's landing gear. This was no longer the sweeping geometry of flight plans and orbital mechanics. It was the measured movement of a suited person through a narrow exit, down a ladder, toward a footpad that had come to rest in lunar dust. The television camera carried the moment to Earth. For those watching, the image was ghostly and imperfect, but it was enough. The world could see a human figure at the edge of a spacecraft on the moon. The event that had begun as a public commitment in May of 1961 had become a person descending a ladder in the Sea of Tranquility. At the bottom, Armstrong paused at the footpad, still partly on Eagle, still not yet fully on the moon. Then he placed his left boot onto the surface. His recorded words became among the most famous ever spoken during exploration. That's one small step for man, one giant leap for mankind. The Apollo Lunar Surface Journal preserves the line with a careful parenthetical. That's one small step for a man, one giant leap for mankind. It notes that the word A was intended, but was not clearly audible in the mission recordings. The distinction has followed the sentence ever since because the intended phrase contrasts one individual human being with humanity as a whole. Yet the power of the moment did not depend on perfect audio. The meaning was plain in the act itself. One person had stepped down. A species had crossed a boundary. Armstrong described the surface as he began to move on it. He was no longer seeing the moon through Eagle's window, or through telescopes, or through orbital photographs. He was standing in the material itself, testing balance, movement, and contact. The landing site that had been chosen for its relative safety was now a workplace, and the first task was to learn what that workplace allowed. Aldrin followed soon after. NASA's event record lists Aldrin on the lunar surface at 109 hours, 43 minutes, 15 seconds ground elapsed time. The two men were now outside Eagle together, while Collins remained alone in Columbia, circling above them. The mission had split into two human experiences that could hardly have been more different. One astronaut alone in orbit, responsible for the command ship, and two astronauts moving carefully near the first human landing site on the moon. The EVA lasted 2 hours, 31 minutes, 37 seconds outside the lunar module, according to NASA's lunar event record. Its duration was short by later lunar standards, but for Apollo 11, it was enough. This first excursion was not meant to roam widely. The Lunar and Planetary Institute notes that the first moonwalk remained within about 60 meters of Eagle. The astronauts were proving that a lunar landing crew could exit, move, collect, deploy, observe, and return. They collected lunar samples, about 21.6 kilograms in all, about 47 pounds of rocks and soil. Those samples mattered because they carried the moon back into laboratories on Earth. The landing itself proved a capability. The samples made the moon available to direct scientific study. What had been a distant body became material that could be weighed, examined, compared, and preserved. They also deployed instruments. One was a seismometer, part of the effort to listen for tremors and impacts through the body of the moon. Another was a laser retroreflector, a device that would allow laser beams from Earth to be reflected back for precise measurements of the Earth-Moon distance. They deployed a solar wind collection device as well, exposing material to particles streaming from the sun. Around Eagle, the surface became a small scientific station, assembled by hand in a place no one had stood before. The equipment was simple in appearance, but its presence changed the meaning of the landing site. Tranquility Base was not only a flag, a ladder, and footprints. It was also a place where instruments had been placed, samples gathered, and observations begun. The first human visit to the lunar surface was brief, but it was not empty. It joined symbolism to work. All the while, time remained limited. Armstrong and Aldrin were outside, but they were still dependent on the systems they carried and the lunar module waiting behind them. Every action belonged to a schedule. Every movement had to end with a return to Eagle. The first footprint could not become a wandering. The mission's deepest requirement was still the one Kennedy had spoken years earlier, not only to land a person on the moon, but to return him safely to Earth. That truth gives the first step its quiet tension. The famous image is outward-facing, humanity reaching another world. But inside the mission, the step was also a midpoint. Columbia was still in orbit. Eagle still had to leave the surface. The two spacecraft still had to find each other again above the moon. The crew still had to cross the distance home. The footprint was not the end of Apollo 11's danger. It was the moment when the promise became visible. After 2 hours, 31 minutes, 37 seconds of EVA, the first moonwalk came to its close. Armstrong and Aldrin returned to the lunar module, bringing the collected samples and the record of their work. Outside, the instruments remained. The seismometer, the laser retroreflector, and the solar wind collection device marked the site as more than a landing point. Around them were boot prints in dust that had lain undisturbed before Eagle arrived. The camera images from that night were grainy, but the historical outline was sharp. A Saturn V had left Kennedy Space Center on July 16, 1969. Columbia and Eagle had crossed the middle distance, entered lunar orbit, separated, and carried out their divided work. Eagle had descended through alarms, passed beyond the planned site, avoided rough ground near West Crater, and landed in the Sea of Tranquility. Then, at about 109 hours and 24 minutes after launch, early on July 21st UTC, Neil Armstrong stepped onto the moon. The first footprint was small. That was part of its force. It did not look like the machinery that made it possible. It did not resemble the scale of Launch Complex 39, or the height of the Saturn V, or the millions of pounds of thrust that had begun the journey. It was the mark of a boot pressed into gray dust. But behind that mark stood the whole chain, the rivalry that sharpened the deadline, the invention that made the route possible, the crews and controllers who trusted procedures under pressure, and the fragile spacecraft that carried 3 men farther from Earth than any human beings had gone before. On the surface, the footprint remained. In the cabin, Armstrong and Aldrin still had work ahead. Above them, Collins continued his lonely orbit in Columbia. And on Earth, the event had already entered memory, not as a simple triumph, but as a moment when engineering, politics, risk, and human presence converged on a silent plane called Tranquility Base.